We are seeing a specific deployment pattern emerge across modern cloud architecture. An autonomous agent scrapes live web data and pipes that extracted text directly into a large language model. To handle this pipeline, engineering teams routinely provision top-tier infrastructure, opting for high-cost GPU instances like the AWS P4D. But in a production environment, the system chokes. The web scraping phase slows to a crawl, creating a bottleneck that throttles the throughput of the entire operation. This creates a massive financial inefficiency. You end up paying $25 an hour for an AI-grade server to run headless Chrome, while thousands of specialized GPU cores sit completely idle, waiting for data. The standard response is to throw larger, more expensive compute nodes at the problem. This fails because it assumes all compute power is interchangeable. Hardware efficiency is dictated strictly by the mathematical shape of the workload. Applying raw processing power to the wrong mathematical structure causes the system to break down. To understand why, we have to define what sequential logic actually is. This applies to any computational process where step B cannot begin until step A is fully resolved. Loading a web page through a headless browser is strictly sequential. The system must parse the HTML, construct the document object model, and then evaluate the V8 JavaScript. None of these tasks can happen simultaneously. Each relies on the output of the previous step. Parallel logic operates under the opposite constraint. It consists of massive arrays of independent calculations that do not require any input from one another. When you run inference on a large language model, you are executing millions of distinct matrix multiplications. Because these independent multiplications do not wait on each other, they can occur simultaneously across a vast grid. Because a browser and a neural network possess entirely different mathematical dependencies, they require entirely different physical silicon to run efficiently. The physical architecture built for sequential logic dates back to 1945, when mathematician John von Neumann proposed the foundation for how a central processing unit handles instructions. This diagram shows the original von Neumann architecture, a central processing unit connected to a single memory block storing both program instructions and data. Because they share one pathway, they must be strictly scheduled. Commands and data cannot transfer simultaneously. Modern CPUs navigate this physical limitation through a relentless, high-speed loop called the fetch-execute cycle. To keep this cycle running without stalling, the arithmetic logic unit predicts the next sequential step, allowing for speculative execution before it is strictly requested. This physical design maps perfectly to web scraping. Navigating a dynamic DOM tree requires the system to constantly evaluate if-then statements and accurately predict the next logical branch. A CPU executes sequential logic efficiently because it dedicates massive silicon real estate to complex control units that manage dependencies, rather than to raw mathematical throughput. Even within the domain of CPU-bound tasks, systems architects must precisely match the hardware to the dependency depth of the workload. This chart maps out a direct physical trade-off in modern server architecture. You must sacrifice high per-core clock speeds on the left to fit a massive number of cores onto a single die on the right. Consider a simulation like finite element analysis. Because the calculation is tightly sequential, it requires extreme clock speeds to minimize time spent on each dependent step. A data point drops on the far left. Extra cores provide zero acceleration. Contrast that with cloud virtualization, hosting hundreds of lightweight microservices. These microservices do not wait on each other. A hypervisor prioritizes total core count to act as independent workers. The individual clock speed of those cores is a secondary concern. Optimal provisioning requires measuring the dependency depth of the software and securing the exact silicon specifications that match it. Which brings us to the graphics processing unit, an architecture that abandons the sequential model entirely. To achieve massive parallel processing, engineers strip away the large memory caches and highly complex control units that allow a CPU to perform branch prediction. In their place, they pack the silicon with thousands of simplified arithmetic logic units designed strictly for rote execution. This layout enables an execution model called SIMD, single instruction, multiple data. The hardware takes one specific mathematical command and executes it simultaneously across hundreds of data points in a single clock cycle. SIMD is the engine behind the heaviest workloads in high-performance computing, from calculating fluid dynamics to training large neural networks. These tasks are simply massive matrices being multiplied billions of times over. They demand extreme memory bandwidth and arithmetic repetition, not complex logic evaluation. A GPU sacrifices logical flexibility to achieve sheer mathematical volume. It is incredibly powerful, but logically rigid. We can now return to the failed AI agent pipeline, where a simple instance of headless Chrome crippled a $25,000 server instance. The browser process failed because the thousands of simplified ALUs inside the GPU physically lack the control logic required to advance the branch-heavy instruction cycle of V8 JavaScript. The GPU cores stall out. They sit idle, waiting for sequential dependency chains in the browser to resolve, dropping utilization rates to near zero. The solution is to abandon a monolithic approach and deploy heterogeneous infrastructure. The pipeline is split in two. The web scraping, DOM parsing, and system orchestration are routed exclusively to a high clock speed CPU node, hardware physically built to chew through sequential dependencies. Once the browser extracts and cleans the JSON data, it passes the payload over to a high core count GPU node, which is kept strictly reserved for matrix math and LLM inference. The financial waste is eliminated because expensive GPU time is no longer burned waiting for sequential bottlenecks to clear. Pipeline throughput scales linearly. In modern computing, securing the most gross compute power does not guarantee performance. Success requires precisely matching the silicon architecture to the mathematical shape of the workload.